Welcome back to ZypherSpaceCore. In the previous episode, we explored Euler-Tolen function and Euler Theorem. Today, we study one of the most famous results in number theorem, that is, Little Fermat Theorem. Many cryptographic system works with extremely large powers without special mathematical shortcuts. Calculations such as 2 raised to 1000, 5 raised to 2000 or even large powers would be practically impossible to handle. Fermat Little Theorem provides a pattern that helps to simplify such computation. So let's begin. So what is Little Fermat Theorem? Fermat Little Theorem is one of the most elegant results in number theory. In the previous episode, we studied Euler Theorem. A raised to 5 of n is congruent to 1 mod n. Euler Theorem works from any modulo n provides that a and n are coprime. Now suppose the modulus is not just any number but a prime number p. For a prime number, we already know that phi of p is equal to p minus 1 because every number from 1 up to p minus 1 is automatically coprime with the p. Substituting this to Euler theorem immediately gives a raised to p minus 1 congruent to 1 mod p. This is Fermat Little Theorem. So rather than completely new theorem, Fermat Theorem can be viewed as a special version of Euler Theorem that works specialized to prime moduli. For a theorem to hold, there must two conditions to be satisfied. First one, p must be prime, and second one, a must be coprime with p. Since p is a prime, this simply means that a should not be divisible by p. Whenever this condition is satisfied, raising a to the power p minus 1 will always produce a remainder of 1 when divided by p. Now let us verify this theorem using actual examples. Let us start with p equals to 5 and a equals to 2. According to the Fermat theorem, 2 raised to 5 minus 1 congruent to 1 mod 5. Computing the power gives 2 raised to 4 equals 16. When 16 is divided by 5, the remainder is 1. Therefore, the theorem holds. Let's try another, that is, if p equals 7 and a equals 3, 3 raised to 6 congruent to 1 mod 7. Although 3 raised to 6 equals 729, reducing it modulo 7 again produce a remainder of 1. The same pattern appears for every prime modulus. This repeating behavior is not a constant. It directly comes from Euler theorem. Since phi of p equals p minus 1 for every p prime, the Fermat theorem follows naturally from Euler theorem. This is why we often say that Little Fermat theorem is simply a Euler theorem specialized for prime numbers. One of the most useful applications of Little Fermat theorem is Primality testing. Suppose we are given a large number and we wanted to know whether it is prime. Direct factorization can be extremely expensive for very large number. Instead, Fermat theorem gives a quick mathematical test. Considering the number 7, we choose a value such as 2 and compute 2 raised to 6 mod 7, the result is 1. Trying another, like 3 raised to 6 mod 7 also produce 1. This result can consistent with what we expect from the prime number. Now we compare this with the number 9. Computing 2 raised to 8 mod n produce 4 instead of 1. Since the theorem fails, we immediately know that p cannot be a prime. 9 cannot be prime. This gives us a fast way to eliminate many composite numbers. However, passing the Fermat does not automatically prove the number is prime. It only tells us the number is likely to be prime. For greater confidence, the multiple bases are tested and more advanced algorithms are often used. Now understand some properties that regarding Little Fermat theorem. First property is that little Fermat theorem is actually a special case of Euler theorem. We already know that Euler theorem works for any modulo n provides the number are coprime. When that modulus happens to be prime number, the Euler theorem simplifies into little Fermat theorem. So rather than being completely separate, the Fermat theorem is actually built upon top of Euler theorem. The another important property is converse idea. If number consistently satisfy Fermat congruence relation for many different values of a, then it appears to behave like a prime number. This observation forms the basis of Fermat primality testing. Instead of directly factorizing huge number, we can test whether it behave like a prime number under modular exponential. Third property is that testing multiple bases increases confidence. For example, instead of testing only a equal to 2, we may test a equal to 3, a equal to 5, a equal to 7. If the number satisfies the Fermat theorem for many different values of a, our confidence that the number is prime become much higher. This idea is widely used in practical primality testing algorithm. Finally, the Fermat theorem can also be written as the alternatively but very useful form, that is a raised to p congruent to a mod p. This version is mathematically equivalent to the standard form and appear frequently in number theory and cryptographic proof. Both versions describe same underlying pattern. When arithmetic is performed modulo a prime number, power gives the following highly predictable cycles, and understanding those cycles is the one of the reason the Fermat theorem becomes such important tool in cryptography. So far, the little Fermat theorem seems to be a perfect tool for identifying prime number. However, the mathematics always interesting expectations. There exists a special case of composite number known as Carmichael number. These numbers are not prime. In fact, they cannot be factorized into small numbers. Yet, they still satisfy Fermat congruence theorem relationship for many values of a. In other words, they behave like prime number even though they are composite. Think of them like distinguish of prime number can trick a simple primality testing. For example, 561 1105 1729, like for the example 561 can be written as 3 into 11 into 17. Clearly it is a composite number, but under Fermat testing it often behaves like a prime number. This creates a problem. If we rely on a Fermat theorem, we may incorrectly classify certain composite number as prime. This is why modern cryptography does not depend solely on Fermat test. Instead, stronger probabilistic tests are used. One of the most popular is Miller-Rabin Primality Test. You can think of like Fermat theorem as a quick first screening test. If number fails in the Fermat test, it is definitely a composite. If it passes, it must be prime, but usually perform additionally test before making a final decision. Despite this limitation, Fermat theorem remains extremely important in cryptography. It helps us in perform primality tests, verifying large number efficiently, simplifying modular exponential, and support RSA key generation. So even though the theorem is not perfect, it remains one of the foundational tools in computational number theory. Let's summarize everything that we learned in this lecture. We started by studying Fermat little theorem, a raised to p minus 1 congruent to 1 mod p, where p is prime number, a is a coprime with p. Then we saw the little Fermat theorem is actually a special case of Euler theorem. Whenever the modulo is prime, Euler theorem is naturally specifies to Fermat theorem. Next, we verified the theorem using numerical examples and observed modular exponential follows predictable cyclic pattern. Then we explored primality testing. After that, we studied key properties of theorem, and finally we discovered the Carmichael numbers. The most important takeaway is that little Fermat theorem reveals the remarkable relationship between prime number and modular arithmetics. A simple mathematical pattern becomes a powerful tool for cryptography, cybersecurity, and computational mathematics. Thank you for watching.